some heat production, and then this heat production will produce some evaporation of this electrolyte solvent, and eventually, if these solvents are also flammable, some fire. So this is one of the main problems with lithium metal is safety due to this mechanism. And in fact, this is the reason why lithium metal has been abandoned, and instead of lithium, we will have a graphite. Okay? However, you understand that instead of this situation, we will have another situation where the passivation film is uniform, and where the passivation film can grow in a uniform way back and forward, we don't have the danger of having dendrites. So if we have a situation where the passivation film is uniform, then we can use lithium metal. And we will see that this, of course, depends from the type of electrolytes that we use. So when we'll discuss about electrolyte, we will see that this possibility does exist. You see here now a very clear picture now of, let me go back, of dendrite formed of passivation film formed for this second situation, where we have some chloride-based electrolyte solution. And you see that here that a very clear formation of lithium chloride crystals. And this is one of most unfavorable situation, because you see that this is a very not uniform film formation. So this is something like here. So this is again some indication of what happens when we will have these effects taking place in the solution. So you see here that what will happen here, for instance, we will have some dendrite formation, and then this dendrite does not go all through the cell, which is good in terms of safety because we don't have any short. However, some piece of the dendrite can fall down. And if they fall down into the cell bottom, they are not useful anymore for the cell operation. So one effect that we have a capacity loss during cycle. Or, as you can see in this case, we will have this situation where the dendrite go all through the cell and shorts the cell. And this is some safety problems. And here you see some pictures of this. This, I think, reports the formation of dendrites, very clearly seen here from the top. And here is a cross-section where you see this situation here. Very big dendrite forming. And this may go all the way through, in this case, or maybe some break, and this would be this case. So at the beginning of the lithium battery evolution, lithium metal was used, but quite soon accidents happens, fire and explosion. So this was, at that time, this was not so clear, but now the mechanism is very clear, and we know now that we cannot use lithium metal unless we are sure that the film formation is very uniform and we don't have dendrite growing. And this is the reason why the technology moved quickly from lithium metal to graphite. You see the graphite as this kind of structure. I think that later, yeah, we will discuss this in more detail later. But and this is graphene layers that can accommodate lithium in and out. I forgot here double arrows, but this is the electrochemical process. Mainly, as I say, lithium ion go inside this structure. Some electrons coming on electronic structure. And you see that the most common formulation here is that the number of lithium that can enter is one equivalent for 6 carbon. So you see this is a graphene layer, 1, 2, 3, 4, 5, 6. So we have one lithium here, one lithium here, one lithium here. Some advantage is that the voltage is very low. This may be is an advantage and a disadvantage. Of course, if the voltage is very low versus lithium, when we use graphite instead of lithium, we don't lose very much in terms of potential. In other words, suppose that the voltage of the lithium TS2 battery is, say, I don't remember, 2.8, something like that. 2.80 volt, okay? When we replace graphite, lithium with graphite, since graphite has 50 millivolts voltage versus lithium, we lose 50 millivolts. So in this case, the voltage will be 2.75. And this is not much a loss, fortunately, right? Suppose that graphite, instead of having 50 millivolts versus lithium, had 1 volt versus lithium, then of course this voltage would be dropped from 2.8 to 1.8. So the fact that this voltage is very low is in this sense in advantages. The capacity is 370 milliampere hour per gram, so relatively high. But we have some problem. As we will see, this electrode operates outside the stability window of any electrolyte. Then there will be also in this case the formation of a passivation film. But in this case the situation is not so dramatic as in the case of lithium metal. We will see this in more detail now. Okay, this is again the structure of graphite, which gives you all the information. And you see that the distance of the graphene is about 246 angstrom, and the open space is 0.334 nanometers, so it's large enough to accommodate lithium. However, only lithium, because if lithium is solvated by the ions, by the solvent, then the solvation will be too big to enter here. So here we see again what will happen for the battery, for the graphite, and now the graphite is tested versus a lithium electrode. So this is a semi-cell, because now we are testing this process. Okay? So, a very common way to test these materials for lithium battery is first to check them versus a lithium anode. in order to see to determine the electrochemical process. We will see this for many materials. Now this is again is the scheme of the batteries in terms of band evolution. Here density of state, here is energy. This is a lithium metal. Again, a lithium metal can be defined by the Fermi level, which is this one. The Fermi level is the energy level that separates filled states with empty states, and it gives the thermodynamic level of a material. Now here we have graphite, and graphite is a semi-metal. Okay, you see, it's in a way also here we have a filled gap and an empty gap. So this seems to be a typical situation of a semiconductor, but there is no any. Excuse me, I take again. Here we see a filled energy states and empty states. But as it happens between a semiconductor, when we have the valence band field and the conduction band field. But in semiconductor, there is a gap between the filled state, the valence band, and the empty state, the conduction band. There is no gap here. So this is very easy to go from one level to the other. So this is why graphite is a semi-metal. So what will happen when and you see that the Fermi level of graphite is here, and the difference between the Fermi level of lithium and graphite gives you the voltage. So the distance is not very high. So this explains why the voltage is only 50 millivolts. When we close the circuit, we will have electrons now that go from lithium into graphite, and this level will decrease, and electrons go in here, the level will increase. So also in this case, like in the case of titanium disulfide, which I have examined before, we will have a continuous decrease of the voltage. However, as we will see this doesn't go with a continuous decrease. In fact, now if we monitor the voltage of graphite versus lithium, we see some interesting effect which we have to explain. First of all, you see we have a plateau here in this voltage profile around 0.8 volts. Now each plateau corresponds to some